Hello. In this video, we are going to discuss about differential equations. Now, the term differential equations, they are the kind of equations which involve they involve unknown functions. They involve unknown functions and one or more of its derivatives. There can be one derivative or more than one derivative, and that constitutes what we call as the differential equation. Now, a differential equation can be of various types, and one such type being the ordinary differential equation. I'll be writing it as differential equation as dE and ordinary differential equation usually written as ODE. So what do you mean by the term ordinary differential equation? Well, it simply means that it is the type of differential equation involving ordinary derivatives. Now, what's ordinary and what's extraordinary, we'll see about that. But this one involves ordinary derivatives, or that which we call as total derivatives. Is there any other type of derivative? There surely is. There are partial derivatives, and that is why we also have the partial differential equation. So the ordinary differential equation is one type, and we have the partial differential equation, which is the other type that we were talking about. So we have the partial differential equation, and that involves the partial derivative, and we have a fair idea about the ordinary and the partial derivatives uh, as of now. So this involves partial derivatives. For example, if we say we have the case where we are taking d2y by dx squared plus some constant 2 mu times of dy by dx, and then we are having omega naught squared times of y, when this is equal to 0. This is the ordinary differential equation where the derivatives are total or complete ordinary derivatives. Whereas, so this is the example for ordinary differential equation. As in case of partial derivatives, we can take the example where we are considering the partial derivative del square u divided by del x squared, where u is a function of x and y, and then further we have del square u divided by del y squared, which is also a function, as it is a function of x and y, so it can be taken as the derivative in terms of x, in terms of y. And we must also remember that while we are taking the derivative with respect to partial derivative, especially when we are taking it with respect to x, the y terms in that given function remain constant or are treated as constant. While we are taking the partial derivative with respect to y, the x terms remain constant. And you cannot simply take the derivative here because u is dependent on both x and y, so we can take the derivative in terms of partial derivative in terms of x and in terms of y, and it is quite possible. But had u been dependent on a single variable, let us say only x, then del square u by del y square or del u by del y in the first place would have given me 0, because there wouldn't have been any y term in it. So that is the basic difference between partial derivative and the normal derivative or the ordinary derivative. So this is the basic difference, but we also come across another term, or the terms especially that we associate or involve in case of derivatives are the uh, order and the degree. Now what do you mean by the term order? Now the order of a differential equation is one which tells us about the uh, highest power, or the power of the power term of the, no, that's not the order, that's the degree. So the order is the highest derivative, the highest number of times the function has been taken derivative with respect to a given independent term. So the highest derivative that appears in a given differential equation. And what about the other term, that is the degree that we have? The degree is the power of the highest order, the power of the highest order that is present in a given differential equation. Now let's take a few examples for your convenience. Now we use some shorthand notations for the derivatives. It's easier that way. d2y by dx squared can also be written as y double primed, while dy by dx, that is the single derivative of y with respect to x, is denoted as y primed. So this is the double derivative term, this is the single derivative term, double prime, and this is the single prime. So we need not confuse it with the powers as 1 and 11. It's simply the double derivative, it's primed coordinates, or the primed not the coordinates but the primed notations. So if we were to consider a kind of equation where we have y double primed cubed plus 3y primed, that is a single derivative, taken to the power 4, and 5y, and this is equal to some value x squared over here, and then the highest the order of the equation that we have over here is second order, because the highest derivative that is present in this equation is the double derivative. So the order is 2. What about the degree? Now the degree is the power of the highest order. Now the highest order, as we know, is 2, and the power of the highest order gives us the degree, which in this case is 3. So now we know what a power and the degree is. In case you might consider the power 4, which is quite high, which is greater than 3, of course, but that is not to be taken or not to be considered, as that is not the highest order. It is the first order, while y double primed is the second order, as we have seen over here. So that is why we cannot really consider. Now if we were to consider just another example for our convenience, let's say we have y double primed to be equal to square root of 1 plus y primed. Now in this case, if we are squaring both sides, because we have to square both the sides, so that we make the equation free from fractional index. So we have y double primed squared to equal to 1 plus y primed, and that is giving me y double primed squared minus y prime minus 1 is equal to 0. It doesn't matter about the right hand side but as of now, but here we have y double primed and it has a power of 2, so the order in this case is going to be 2 and the degree is going to be 2 as well. So these are some of the ways where we can find the order and the degree of a given differential equation. Now we move to a new topic, that is an important one too, that is the linear differential equation, or in short LDE. Now the linear differential equation is the type of differential equation where the dependent variable, now as we know that a derivative comprises of dependent as well as an independent variable. In case of dy by dx, y is depending on the variation in the value of x, which is independent, so there y is the dependent variable. So in this linear differential equation, what we are getting is that the dependent variable and all its derivatives occur in the first power without a product of the dependent variable and a derivative, without the product of the dependent variable and a derivative. Now what does that mean? So suppose for example we have let's consider the first order linear differential equation, where we are considering the case that is y prime x, that means it is dy by dx of course, plus p, which is a function of x multiplied with y, is giving fx, a function of x. Now as we already know, y prime of x, it means dy by dx, and y is simply a function of x as well, so y is the dependent term. Now as you can see over here that y, the dependent variable that we have, the dependent variable here is y, and all its derivative, they occur in the first power. That means the power is 1 over here. Power is 1 in this case. So the power is 1, that's for sure. And without a product of the dependent variable, so the dependent variable, that is y, without a product of the dependent variable and a derivative, so without a product of y and the derivative. Now y is multiplied to px for sure, but that is not a derivative term, so the dependent variable is just multiplied to another term which is dependent on x, but they are not. So this is the first condition that we studied over here as the first power, And then we have the second condition over here where the dependent variable and a derivative. So this is the second condition that we observed over here. So they are completely uh, okay, and they therefore this equation that we have over here defines the differential equation. Now we can have the second order differential equation as well. So the second order differential equation, linear, that is linear differential equation, will have the double derivative, that is y double prime x plus px y primed, which means the derivative of y along with that, along with any function of x. And then remember the product of the dependent variable, that is y, with no derivative term, simply qx, and that is equal to some function of x on the right hand side. So this is the second order that we considered. Now if we consider the right hand side, now if fx is equal to 0, then the differential equation, the linear differential equation, is called a homogeneous equation. While in case fx is not equal to 0, then it is known as the inhomogeneous linear differential equation. So that's a way of denoting those two equations, that is in the form of homogeneous or inhomogeneous, depending on the value on the right hand side. If it is equal to 0, it's a homogeneous equation, and if it is not equal to 0, inhomogeneous. Now the constant terms that have been multiplied, that is px and the qx terms, those are constants, and for a given ordinary differential equation they are called as constant coefficients. Now because they are functions of x, they may vary with the value of x, and when they are varying with the value of x, they are known as variable coefficients. So they are constant coefficients when they remain constant, means the value does not change when they remain constant. May so happen that they are dependent on x, but not explicitly in the equation. So in that case they are just numbers, and multiplied with x to the power 0. So x to the power 0 is 1, so in that case they remain constant. But if they are varying, they will be called as variable coefficients if they change their value with respect to x. That is the independent term, which is x. It changes independently, and as a result of that, the derivative term as well as the coefficients that have been multiplied, they may change. So it depends. We'll see examples of that pretty soon. Now, having discussed about the homogeneous differential equation, let's consider the case of function which is homogeneous, just to know the difference of what we may come across while we are studying various terms or various um, aspects of equations. Now the function f, which is dependent on x and f, which is dependent on x and y, is called a homogeneous equation of degree n. Well, it's not an equation, it's a function, so it's a homogeneous function of degree n if we can represent it as f. Supposedly we multiply a constant lambda over there, so lambda x and lambda y is going to give me a lambda to the power n f of xy. Now then it will be a homogeneous function of degree n. Let's take an example. So let us have the function fx y to be equal to x cube minus x squared y. Then, as per this rule that we have just discussed, then we put f of lambda x lambda y, that will be equal to, instead of x we'll be having lambda x cubed minus lambda x square multiplied to lambda y. And then in this case we have the lambda cube x cube minus the lambda square, and the lambda from the y is also going to give me lambda cube times of x squared y, or we can take the lambda cube away from as the common term, and x cube minus x squared y. So this is lambda cube f of xy, which was chosen initially in the given as the given function. So because x cube minus x squared y is what the function that we had. So here we have the equation or the function which was given, x cube minus x squared y is a homogeneous function of degree 3. Now it's quite clear from this analysis that we just made that the concept of homogeneous function and homogeneous equation are pretty different. They need not be the same, they are different, because in this case you are obtaining you're not taking any derivative, it's just the given function, and you are just involving a constant term which is producing the degree that we wish to find. But in case of a homogeneous differential equation, we have to consider the highest order and the power term of it, then we get to know about the degree of the equation. So these are quite different things. In case there would have been any confusion, I just cleared it by making a special reference on this topic. Now let's consider a linear differential equation where we have y of x to be equal to, it's not a differential equation, it's just a simple equation. We'll get the linear differential equation out of it. So let's see. So the equation is something like this: y of x is equal to ax squared plus bx plus c. A, b, c's are just the arbitrary constants. Now if we take the first derivative of y with respect to x, then we have y prime to be equal to 2ax plus b. Then if we take the double derivative, y double prime will be equal to, that means we are doing the derivative the second time on y dash that we have obtained, and that will result in 2a only, because there's nothing else left. Now further, if we take the third derivative with respect to x, then we are going to end up with 0. So that means that this particular equation that we see over here, it is a third order linear differential equation, and it's homogeneous as well because the right hand side is 0, so it's homogeneous. Now the equation and this ax squared plus bx plus c is called the primitive form, and or in short the primitive of the differential equation. So this is the primitive of this differential equation that we just obtained. And we also note from this that as this is constructed, as this equation over here, the differential equation that is, as it is constructed, the a, b, c, which were the arbitrary constant terms, they were eliminated. So here a third order equation is constructed by eliminating 3 arbitrary constants involved in the primitive. So in general, a primitive involving n essential arbitrary constants will give to a differential equation of the order n free from the arbitrary constants. So that is what we get to know, that for an equation involving n essential arbitrary constants is giving rise to nth order differential equation. Now if we were to integrate this once again, this third equation that we have, so y triple prime, that is, and we integrate that. On integration, we'll be getting y double prime of x to be equal to some constants, let us say a primed. It's a constant of integration. Then again, if we further integrate it, we get y prime to be equal to y prime of x. Obviously we need not be writing x every time because we know that we are integrating. Just for the sake of integration, I have included the x over here, but I had not done so on the previous occasion while taking the derivative. So y prime x is going to be the a prime that will be multiplied with some x, and also we add an integration. I'm not going completely in steps, I'm just writing it down as we are quite sure about the integration and the derivative part. So a prime x plus b. In case of any confusion related to integration or derivative, you can check for the videos that I have made on them, especially in the motion in a straight line part. Then if we do the integration further, we have y of x to be equal to, now this involving an x over here is going to be x squared by 2 as we do the integration further. So we end up with yx to be equal to a prime x squared divided by 2 plus bx plus c. So now if we compare this equation with this equation that we just obtained, the left hand side is the same, that is yx and yx, so it's only about the right hand side. So we get a to be equal to a prime by 2, and both are constants, so there's no problem with that. Both are just constant. One is an integration constant, one was the arbitrary constant that we had given in the previous equation. Now we observe that the primitive that gives rise to the differential equation is once again recovered when the differential equation is solved. Now in general, the problem of solving a differential equation of n, of order n, involves finding a relation between the variables involving n independent arbitrary constants, which together with the derivatives obtained from it satisfy the differential equation. Now let us have the most general linear differential equation of nth order, and it can be written in the form dny by dx to the power n plus a1x dn minus 1y dxn minus 1 plus, and it goes up to an minus 1 of x dy by dx, finally having an of x multiplied to y is equal to fx. Now this is the nth order linear differential equation. Now this is also this can be written as Ly is equal to fx. L is the linear differential operator. L is equal to dn by dxn plus a1x dn minus 1 dxn minus 1, and then it continues up to, I'm writing just the last term, not the previous one, anx, and that's it. That's the linear differential operator for you. When it operates on y, you end up with fx on the right hand side. Now this may have a solution. Let us say if y is equal to u of x is the solution, just like in the previous case where we had like this equation where yx was something and it led to some differential equation that is here. Similarly, we can have y to be equal to u of x, where u of x satisfies the above equation of the nth order. Well, then we say that y is equal to ux, or the ux is the solution to the equation. Now if fx that we have on the right hand side is equal to 0, then we can consider the y to be having a solution yh as the solution, and then we can use it in the equation as L, the linear differential operator, acting on yh, giving out a 0, and this is the homogeneous equation because fx is 0 in this case. So now if we say this is of nth order, so we can take, let us say, u1x, u2x up to right up to unx are the solutions. There can be n solutions, so let's assume that these are the solutions of the nth order linear differential equation. Then when we operate the linear differential operator on these individual equations or these individual terms, then what we are definitely going to get is L of u1 of x is definitely going to be equal to 0, as u1x is the solution of it. Now even if we multiply a constant term, that is, let us say c1, to that, it won't make any difference because that's a constant. It may carry a constant. In case it does not, then the constant is simply equal to 1, so there's no problem with that. Similarly, for L acting on u2 is going to give me 0, and we can again multiply a c2, which does not really make any difference except for a constant value, and likewise we can have terms right up to LCN for the nth term unx is equal to 0. Now if we add up this entire equation, we are still going to end up with 0 on the right hand side. So we have L of all those terms added, that is C1U1 plus C2U2. We know they are functions of x, so we need not write that every time, plus CNUN, and that is going to give me 0. So because we had considered L of YH, so we can say that YH is equal to, it's no space there, I'm writing it over here, L of YH was equal to 0. So YH can now be taken as, YH will be equal to all those terms summed over. Let me just take it as CK UK, and the UK's are always functions of x as you know them. So k here going from 1 up right up to n. So this is the general solution for this nth order differential equation in the homogeneous form. Now we take y equal to yp as the solution for fx not equal to 0. That means it's a finite term, it's not equal to 0. Then we end up with an inhomogeneous equation for which we have Lyp to be equal to fx on the right hand side instead of 0 as in case of the homogeneous equation. Therefore, if we add up these two equations, this one and the homogeneous one, so we end up with Lyh, which was giving me 0, plus Lyp, which is now giving me fx. So on the right hand side, 0 plus fx is going to be fx. Or together what we can write is L of YH plus YP is equal to fx. Now remember that we had the initial equation as Ly to be equal to fx. So that means that if we compare these two equations over here, so we get y to be equal to YH plus YP, where YH and YP are the solution to the required differential equation, which also means that the solution of the inhomogeneous differential equation, linear differential equation, consists of two parts. The first part being YH as the solution to the homogeneous equation, and it is known as the complementary function. When it is the solution of the homogeneous equation. Then we have Yp as the particular solution of the inhomogeneous equation, and therefore it is called as the particular integral. These are the terms that we relate with a differential equation, ordinary differential equation in the linear form. And in case the equation is completely homogeneous, you have only YH as the solution. In case the equation is inhomogeneous, you include two parts, that is the YH, which is the complementary function, and the particular integral. Now we aim to discuss briefly the methods of solving the first order and the second order differential equations of degree 1. So let's proceed. So this is the entire structure that we are going to discuss, that is the first order differential equation in its simplest form in the first case, followed by the variable separable case, the exact equation, and the inexact equation involving the integrating factor, which is multiplied to the exact equation to make it, which is multiplied to inexact equation to make it exact, And the general first order differential equation after having studied the simplest form in the first place, and the Jacob-Bernoulli equation, uh, form of the first order differential equation, useful in mathematical and physical approach. Then we move over to the second order differential equation. We discuss the differential operator along with the solution and the linear independence, which is easily explainable by means of the Wronskian, an interesting mathematical tool for us. And then we have the homogeneous second order differential equation with constant coefficients involving the auxiliary or the characteristic equation. To end it with homogeneous nth order differential equation, and then the last but not the least, the inhomogeneous linear equations and the various methods, the operator methods that we can involve to obtain the solutions. But that will be discussed further in the next video without further stretching this video a bit longer. So stay tuned for that. Till then, thank you for watching.